whenever you are going for interviews, where the emphasis is always on the basics. And remember that most of the time basics come by the knowledge of a very simple things. For example, you can be given a simple function like a mathematical function, square root x. Does it qualify to be a wave function in the space from minus infinity to infinity? So that means that you do need to know the properties which wave function generally follows. It's a continuous one. The first derivative has to be continuous one. I mean, you know that wave function cannot take two values at any particular point. So you may be asked to just draw a function root x and things like those. So it is important to study from that perspective, where ultimately we are applying the concepts, but the concepts are clear at the fundamental level and not at only the advanced level. So sometimes what happens that you are doing something like vector spaces, you are doing inner products, you are able to solve several complicated problems which may not be solved by students who are at the BSc level. But are you able to define something very simple, just like the way we say, what is vector? Can we make it independent of the coordinate system in terms of the definition? So we do need to know certain properties of the vectors, surely. Unless until we know those properties, we cannot say that. But we will have to just keep on reading more, little bit more advanced books. Again, I will emphasize that I found that at least in the Balakrishnan book, it tried to emphasize on the basics and then it builds onto it. So I cannot expect you to read the whole book, and it is not there even in the syllabus. But whatever is there, at times you can just browse through the pages. You will be able to get a lot of things from it. Anyway, for the class, since we have to do that, so let me just continue with it. Are you able to see the screen?
Yes, sir.
Yeah.
Yes,
So
Yes,
somewhere
sir.
yes, sir.
last class we discussed about the Dirac notation, the bracket notation, and the word ket, which came from that. Remember that for all mathematical purposes, the two notations are same. It is just that the way Dirac interpreted that it, I mean, for the Dirac's interpretation, we have the ket space and the dual bra space or the adjoint space, which are two distinct spaces, but they are related. That to every ket, there exists a bra vector, something like that. Then we came up with this concept of the linear transformation or mapping. Remember, we are basically trying to implement it for quantum mechanics. So now we are going into the regime of having the physical observables. We were always talking about the state of the system thus far when we were talking about linear vector space or the inner product. Now what happens when we make a measurement? When we make a measurement, it is equivalent in the linear algebra that a linear operator is getting applied on that wave function. So we are making a measurement on the state, and of course the results will come and we will see how it goes further. But let's just build the fundamentals. So I defined linear operator which takes from the same vector space to the same vector space, which means my vectors are not going out of the space. We did few examples, and towards the end I tried to show you or just tell you that once a basis is given, then this operator can also be represented by a matrix which we wrote. And remember that the first column corresponds to the column vector of our first TU1. I mean, that is something which we'll have to remember. And at the last thing which we did, that it is immaterial whether we apply this linear operator on a vector and then construct the matrix, or we first construct the two matrices and multiply it. So now that we are doing this kind of abstract notation, so let's have one simple example to understand it. So I am just actually I was just writing down that example. So let's consider we are going from R square space to R square such that there exists a vector in this space with a simple coordinate x, x comma y. So, okay, so let me just write down. And the operation, the T operation on it is such that the resultant would be 2x plus 3y, comma 4x plus 5y. So, okay, minus 5y. Doesn't even matter, but yes, I mean, ultimately we'll have to have all the things with this. So a question can come up with this. So first, let me just explicitly write down this tu, which is equivalent to acting on t of xy, gives me the vector in the same space 4x minus 5y. Sometimes you see it like this. And now my first question is rather simple. I want to find out that, let's say, if there exists a basis will have two vectors, of course, which is 1 0 and 0 1, the standard orthonormal basis, and I want to get the representation TS. What will be that? So first is the matrix representation of this operator in this basis. So how to go ahead with it?
Sir, we can operate T operator on E1.
Okay, so let's just do that. So operate T on E1, which is equivalent to saying T on 1 0. So what is the result?
2 comma 4.
2 comma 4. Okay, and then what?
Then for E2.
Yeah, but I need to expand this in terms of my basis vectors E1 and E2 in
Write
order
them in
for.
column.
So I can simply write down as 2 1 comma 0 plus 4 0 comma 1. This is, since it's a standard basis, or I mean, you can remember that the way the usual one, I can write down like this. What about TE2? This will be T01. Result will be
3 comma minus 5.
3 comma minus 5. Rather simple. I mean, you can write down the rest of the thing. 310 plus 3, sorry, minus 501. So keep a pen and paper ready, because this is the simpler one and I am going to just make little difficult, not of course a very difficult one. So let's just try to write down now the matrix. So what will be this? So 2 4 3 minus 5. What should I write? The first.
So 2 4
2
along
4
the
will be
column,
the first
Column.
2 4 and 3 minus 5.
3 and minus 5.
Yeah, with respect to the standard basis, which is standard orthonormal one, actually, if you look at it, this becomes rather simple. That 2 4, what we got for the first one, that came as the first column, and 3 minus 5, that came as the second column. Looks rather standard. Okay, let's continue. So a general vector in this one, that will be represented by two numbers, 3 minus 7. What about this guy? Matrix representation of the column vector.
3 minus 7.
3 minus 7. So let's apply what we did yesterday. So let's try to find out TS. This will be what? 2 4, sorry, 2 4 3 minus 5. What will be the result of this matrix multiplication?
Minus 5.
Minus 5.
No, sir, minus 15 and 47.
Minus
Yes,
15.
sir. Same as Isha.
Minus 15 and 47.
Yes, sir, minus 15.
And this, of course, 2 3 is 6, minus 7 2 3 to minus 21. So this will become minus 15, 47. And okay, we have got some result. Now let's compare it with something where we apply T on this V, or the way I am writing. So let's just apply this. So what will happen to this? So I am basically now trying to write down 3 minus 7. 3 minus 7. So what will be the result of this? If I apply my operation T, operator T, on this vector V, which is 3 minus 7. So use this relation.
Minus 15, 47.
Minus 1547.
Yes, sir. The same one.
Minus 1547, which means that if I am going to write T, V, this, you are going to get minus 1547, because in the standard orthonormal basis, whatever comes as the two numbers, they just follow there. It looks rather trivial, it looks rather simple. Let me make your life a little bit difficult. So I switched to a different basis, and here I am using two vectors. Again, since it's a basis, so it will have to have two vectors. And instead of having this regular orthonormal basis, I am going to give you 1 comma minus 2 for u1, and for u2 I am going to give you 2 comma minus 5. So now question number 1, will this make a basis in this vector space R square?
Yes, sir.
Yes, sir. It will.
Yes, sir.
How did you figure out?
They are linearly
Sir,
independent.
because it is
So they are
maximum.
independent
maximum
and it spans.
Linearly independent.
Maximally linearly independent. Very good. So this will make. Now I want to do exactly the same thing. First, I want to write down my in this S prime. So matrix representation, but now in this S prime basis. So how are we going to do? So let's just do it explicitly so that everybody understands. So T acting on U1, which means you are going to put 1 for X and minus 2 for Y, and just get whatever you get. Result.
Sir, it is minus 4 comma 14.
Okay, let me wait for others to also say that. Minus 4 comma 14. So all you are supposed to do, this is for everyone, that you are going to put X is equal to 1 and Y is equal to minus 2 in the expression of our Txy. Anybody else who would confirm it?
Yes, sir. It's getting.
Yes, sir. It's the same.
Yes, sir. It's
4 comma. Minus 4
Yes,
comma
sir.
14.
Right. Minus 4 comma 14. Now how am I going to write it in terms of my vector u1 and u2? So
So
I
again, we
want
can
to
do alphas multiply
alpha 1 u1, very good, plus
and then put it equal
alpha.
to that.
Yeah, please do that then. So all of you, please understand what we are going to do. We want to expand the result, which is nothing but a vector in the same space, in terms of the new basis. And whenever we are expanding this vector in terms of the new basis, whatever the coefficients alpha and alpha 2 come, that is what we are interested in figuring out, because that's the component which will go in my matrix. So let's just try to figure out that. So I can write down explicitly alpha 1 comma minus 2 plus alpha 2 2 comma minus 5, so that the two equations which will come for you is, it will be alpha 1 plus 2 alpha 2 is equal to minus 4, and next equation will be minus 2 alpha 1 minus 5 alpha 2
Minus 5.
is equal to 14.
Sir, alpha is 8 and beta is minus 6.
Oh yeah, so the way I write minus 8 u1 minus
Alpha 2
6
is minus 6.
u2. This is what you are getting.
Sir, first one is plus 8.
Okay. Oh, alpha is 8. You did say that. Okay. Let me just wait.
It's the same, sir.
8
Yes, sir,
minus
same.
6. Third. Okay.
Yes, sir.
Yeah. So those who have answered, I mean, I would like them to now wait, and I will let others also respond. Let's do the same thing because we have got the first column of the matrix, which is 8 minus 6. I want the second column also, which means I should be able to do T of U2, and whatever comes, I should be able to write down in terms of, let's say now, beta 1 U1 plus beta 2 U2. So I request others to please chip in and try to give me answers. So T U2. That means that I am going to put 2 and minus 5 for x and y respectively. What will be the result if I am going to put this operation?
So it is minus 33 and 11.
Minus 11, comma
11,
33.
Minus
Minus 11,
11,
comma
comma 33.
Sir.
Thank you. Thank you.
Sir,
Yes. It is opposite.
No, sir, it's fine.
No, sir, it's fine. Minus 11, comma 33.
Minus 11, comma 33. Now expand this in terms of your u1 and u2 vector, which is the basis vector, and get the value of beta 1 and beta 2. So let me just go to the next page. Beta 1, beta 2. Others, please continue doing this so that we understand how we are working on it. This is what we have already got.
sir, alpha 1 is plus 11 and alpha 2 is minus 11.
Yes.
Okay, so
Yes.
11 minus 11.
Yes, sir.
Okay, fine. So at this point of time, I hope you get the important thing which is coming out. It is not only important to get the application of T, but it is also important, equally important to expand it in terms of the basis vectors. So let's just do the question, continue with our basic question. So next part, given V is equal to 3 minus 7, I am interested in, of course, finding out what will be this V with respect to this new basis. So I want to write down 3 minus 7 in terms of my new basis U1 and U2. And for all of you, let's just go back. Remember that U1 and U2 which are given here is 1 minus 2 and U2 is 2 minus 5. So write down 3 minus 7 in terms of your new basis.
Minus 53 and 59.
Okay, let me minus
Minus 53 and 59.
minus 53 and 59. Okay, let me wait for others to also respond.
Yes, sir. It is minus 53 and 59.
Okay, so how did we do that? 3 comma minus 7. We wrote, let's say A1, 1 comma minus 2.
No,
Plus-
sir, I'm getting 1 comma 1.
Yeah, that is
Yes,
why
sir,
I'm
1
asking.
comma
It is
1.
1, 1.
Yeah, so that's what I am
1,
trying to figure out. So you must have got A1 plus 2A2 is equal to 3, right? And minus 2A1 minus 5A2 is equal to minus 7. These are the two equations which you must have got.
Yes.
Yes.
So, but if I just do 2A1 plus 4A2, which is I am writing my first equation, basically multiplying twice and adding the 2. So I should be getting what? Minus A2 should be minus 1, is it?
Yes,
Yes,
sir.
sir.
which means A2 comes out to be just 1,
Yes, sir.
Yes, sir.
which means my A1, which is 3 minus 2A2, should turn out to be
1.
just 1.
1.
So those of you who have got it, I mean, can they just check again? Why two of you
So I made a
independently?
mistake. What I did
Okay.
was I found T V, matlab T
Aha,
applied on
right,
V.
right, right,
That
right.
matrix.
That's what I could have thought of. So this is not what we were asking for. We asked for simple this component vector in this new basis. The whole idea for you to do this maths, because ultimately maths is an applied one, and we have to do these things in future very commonly. So let's just continue. What will be T of S prime now with V of S prime? So you have got first matrix here and you have got second matrix here.
Yes, sir. This one is minus 53 and 59.
Okay, so let me just see whether you will get it or not. See, 8 minus 6, 11 minus 11, right? And you are multiplying it by 1, 1. So
I
this,
don't think
Sir, it is 11, 19 or minus
19. Yes, sir.
so this should come out to be 19 minus 17. So there must be
Yes.
some other mistake also in terms of the calculation. Are all of you getting 19 minus 17? I am hearing two
Yes,
people.
sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir. Yes, sir. Got it now.
Good, good.
Yes, sir.
And let's just apply it now. First apply this T operator on this V, so that now what we have got again, this number we got last on the last page. T acting on V, this came out to be minus 1547. Okay. What are we supposed to do to this minus 15 and 47?
Write it in the new basis.
Right. So please write it in the new basis. So B1 U1 plus B2 U2. So that I can write down T V S prime.
So we are getting the same 19 and minus 17.
Very good. You are getting the same, which is 19 and minus 17. Others, let's see.
Yes, sir. We got the same.
Okay. So at this point of time, what I wanted to say is one important thing, that please understand how to apply your formula also, the one which we are getting. This relation, the relation which I wrote on the previous page, the last relation, that is valid in all bases. It is just the important point that the basis, if you look at one, I mean, linear operator in one basis, it looks like 2, 4, 3 minus 5. Look at the linear operator in the other basis, it is 8 minus 6, 11 minus 11. So the same operator which is given by one set of components in one basis is given by totally other components in other basis. Even though the operator remains same, the action of the operator on this vector space remains same, but the components change. So are these two related, by the way? Can somebody tell me, is there any way to figure out if this guy Ts prime related with this guy Ts? Or for that matter, just look at the vector itself, 3 minus 7, generic vector, which had the components written as 3 minus 7 in my first basis. As soon as I go to the next one, I find that the components are written 1, 1. Are they related? I mean, ultimately they are representing the same thing, right? Anybody? Okay, so this is what we are going to see as the next thing. But one thing which becomes very common from now onwards or otherwise, we have so many bases for a given vector space, and we will also always be performing actions from one basis to another basis. So we are now going into something what we call as change of basis transformation or operation, where what we are interested in doing is to go from a set of bases, let's say S, which we call as our first basis, UI, to another basis S prime, or maybe come back from one basis to another one. So this is something, as the name suggests, transformation. This is also falling under the same category of linear transformation or linear operation. Since we are staying in the same basis, so we of course call it as an operator and hence the operation, but transformation is a generic name for the same. Right? So let's just try to see how to perform this change of basis transformation in general, so that in future if we are changing the basis, we should always be using that change of basis transformation to apply on a vector or apply on a linear operator and then get the new result. So let's just look at this special one. So for the simplest example, I always come up with this V2F, which is the two-dimensional vector space over a field, which can be easily extended to any V and F. Fine. So let's just do that. So we have two vectors in this one in the first basis of this vector space, and another set of two vectors in another basis of the same vector space. And since they are all the vectors of the same vector space, I can always expand, let's say W1 as alpha 1 U1 plus alpha 2 U2. Since of course W1 is a vector of the vector space and S, the set, is the basis, so I can expand that. That's the property of the basis. And I can expand another one also. Fine. So what I define as the change of basis is a matrix which is made up of these components. So I define a matrix where I am going from set S to set S prime. Please look into the notation. I am using a particular notation. As long as you understand it, you use it. In case if you do not, then I can ask you to even switch to other thing, because several books use several ones. As long as the concept is clear, that wouldn't make a difference. But let's just stick to one notation. So I'm going from one basis to another basis, S to S prime. And I want to write down the matrix of the component. So how should I write down? So I have first matrix, first column made of alpha 1 and alpha 2, which is the way I wrote my linear operator, remember? And the second column will be beta 1 and beta 2. Okay. So simply, just like the way you define your linear operator, we define a change of basis matrix. And this matrix will allow me to go from this S to S prime. Now, what happens that if we have a general vector in this vector space, let's say, which is written in terms of the new one, gamma 1. So I have a vector which can be written expanded in the first basis or which can be expanded in the second basis. Now, of course, there are many bases, so I can expand it in any of the bases. So let's say vector is given in this basis. So can somebody tell me what should I write as the matrix? So this V is given gamma 1 and gamma 2 as the two components in which basis, S or S prime?
S prime.
S prime, of course, because it is W1 and W2. So of course we have expanded it with respect to W1 and W2. Yeah. So let's just see what happens if I apply Ps to S prime on this S prime. So I have this alpha 1, alpha 2, beta 1, beta 2 multiplied by gamma 1, gamma 2. The result will be alpha 1, gamma 1 plus beta 1, gamma 2, alpha 2, gamma 1 plus
Beta 2 gamma 2.
Beta
Beta 2 gamma 2.
gamma 2. Thank you. Okay. Now, let's just try to write down the same V in S. So, how to do that? I have my gamma 1. What is this W1 vector in terms of my first one? It is alpha 1 U1 plus alpha 2 U2. Right? Gamma 2 will be beta 1 U1 plus beta 2 U2. Those of you who can follow yesterday's lecture, it is very similar to what we did for a linear operator, but okay, still we are continuing with it. Please collect the terms of U1 together and collect the terms of U2 together. So this is U1 and U2. So what will be the term which I should write here? What should be the term which I should write here? So this is alpha 1 gamma 1 plus
Gamma 1
Beta 1,
gamma 2
beta 1, gamma 2.
yeah, and you understand that
Gamma
it
2
doesn't
beta
matter.
1.
I mean, since these are the numbers, so I can write anyone first and anyone later. Yeah. Okay. What about the next one here?
alpha 2
Alpha 2 gamma 1
Alpha 2
and
gamma
beta
1
2
plus
gamma
plus
2.
beta 2 gamma 2.
Beta 2 gamma 2. Now, look at this. This is what we are writing. This is not the matrix representation, so I should just correct this. I am interested in getting it, but this guy is just the vector, which is written in terms of this basis. New now written in terms of the new basis. So let me just see what will be this guy V of S. This is what you have written. Now expanded in terms of the first basis. Alpha 1 gamma 1 plus beta 1 gamma 2, alpha 2 gamma 1 plus beta 2 gamma 2. Now look into this guy. This is exactly what you have got. Ps to S prime. So if I apply my change of basis transformation on this vector in this S prime, then I will get the vector in the S state or in the S basis. So instead of now thinking of writing my or expanding my generic vector in terms of new basis, I should be able to find my change of basis transformation. I apply it such that, please follow this notation that I am applying it on this S prime to S prime. So Ps to S prime on this V S prime, and I get this new one. So every time I am doing a change of basis, it is equivalent to saying that I am coming up with a corresponding matrix which will allow me to do this change of basis. And hence the matrix which represents this is called the change of basis, or I write it as P. Yeah, okay. Now, I could have asked this question in other way also. So let me just continue building on it if we understand it properly or not. What
This
if?
what we call
Yeah.
transition matrix?
Yes. Yeah, this is what we call the transition matrix. I mean, as long as we understand it is the basis which has changed now, right?
Yes, sir.
So basis change, I mean, the simplest one is change of basis because we are changing basis. Transition word generally applies to that, but one has to be clear that we are talking about the basis change because this basis change will result in the change in the components of a generic vector, right? And now I can
Yes.
apply this and I can get it for new one. So it's still building on to that, right?
Sir, so this means that this matrix can be used to transform from one basis to another. Like from S prime to S also and vice
Yes,
versa.
yeah. So I'm coming to that. I'm coming to that. So I could have, so that's what I am trying to say, that I am building on to that. What if I would have been given my first basis, let's say in terms of the second one. So instead of, look at the way I am writing it, earlier it was W1 and W2 given in terms of U1 and U2. Now I'm writing U2, U1 and U2 given in terms of this. So question 1, are these A1, A2, B1, B2 somehow related with those alpha 1, alpha 2, beta 1, beta 2, which I showed on the previous page? So
Yes, sir.
where W1, so who is going to help me out giving that? I can, let's say, write, I am writing it, Q S prime to S. So something similar to P, but last time I was writing S to S prime, but now we are going from this space S prime to the state which is now our original one, the S1. So what should be the matrix of this? Of course, A1, A2, B1, B2. But I want to write it in terms of my alpha 1, alpha 2, beta 1, beta 2. Can I do that?
It will be the inverse of that matrix.
So how will I find out? But what you should be able to find out, that this matrix should turn out to be alpha 1 beta 2 minus alpha 2 beta 1. Then what should I write here? It should be
Adjoint.
beta 2 alpha 1. No, not adjoint. It is just what was said earlier. This is basically same as P inverse S to S prime. How will you do that? So let's just take it as a simple homework. It's not a big deal, of course. U1 is now given in terms of A1 W1 plus A2 W2. U2 is given B1 W1 B2 W2. Now look at the expression which was given here earlier. W1 was given in terms of alpha 1 U1 plus alpha 2 U2. W2 was given in terms of beta 1 U1 plus beta 2 U1. So if I want to write U1 in terms of W1 and W2 and U2 in terms of W1 W2, you have to just do some simple linear algebra where you will be multiplying maybe. So in order to remove this U2 term, you may be multiplying the first one by B2, second one by maybe alpha 2, and just subtract the 2. You should be getting the first U1 and so on and so forth. It's a simple 2 by 2 linear algebra. If you are not able to do that, you come to that, but let's just focus on the important point. That if I do the inverse, I mean opposite, instead of now going from S to S prime, if I'm going from S prime to S, then the matrix which is involved is nothing but the inverse of the previous one. That's it. And what does that mean? This means that I can now apply this P inverse S to S prime on a vector in S to get S prime. Now, just to make life clear, so let's see that I'm going from S to S prime, or I can come from S prime to S. So if I have my P S to S prime and P inverse, which of course get built from S to S prime, once you have P, then the operation of this guy on S prime result in S, and operation of this guy on S result in S prime. In fact, this was rather clear from the first expression itself. If you just take the P inverse operation S into S prime on the first one, you will get this V S prime, and here you will get P inverse on this V. So it works both ways. The catch which generally happens when you are solving your numericals, the catch comes in that I could have written it in this manner: S prime to S inverse, and that's why I'm going to solve a problem and then see how this guy works. Yeah, I mean, it is basically remembering that my P or Q is equal to P inverse. As long as you remain consistent with your notation, everything works well. Once you become inconsistent, for example, you are finding out one matrix and then you are using different relation, then we will be out of it. So what best to do? Let's just do an example and see if we understand this portion. So please use the notation. I mean, I have a habit of using it. You can use whichever way you want to, but try to be consistent in terms of what we are doing. Let me just make a problem and then we'll solve that problem to understand that how it works. Fine?
Yes.
sir.
So let's say, remember, this is what we did in our previous case. We had this S which was made of two vectors in our R square, and we also had this S prime which was also made of two vectors, and these U1 and U2s were
One minus two,
1 minus 2,
2 comma minus 5.
2 comma minus
Minus
5.
5.
Okay, so these are the two ones, right? 1 minus 2 for this one, the 2 minus 5 for this one. Yeah, okay. Now I want you to write PS to S prime. So what am I asking you to do? I'm asking you to write U1 in terms of E1 and E2, and similarly U2 in terms of E1, E2. So give me the coefficients here. U1 when expanded. So what is the first coefficient which I should write?
1.
1
1, and here
Minus 2.
minus 2, and here
2.
2, and then
Minus 5.
Hence minus
minus
5.
5. Remember, this guy is the rather simple one. Why? Because this is the standard normal basis in terms of which I am writing, and hence this may be a simpler one. So let's just write PSS prime, S to S prime. What should be this then? This matrix.
column
First
the-
1
column.
2
Writing them
1,
in columns.
2
right? So 1 and
2
minus 2. See,
minus
the
2
first,
sorry. 1
right?
and minus 2
Absolutely
2
right.
and minus
And
5
then 2 minus 5. Okay. Okay, makes sense. And then we use a vector V. How that vector was defined in general for the two component vector?
Gamma 1 times W1.
Yeah, but what were the numbers which I gave to you?
3 minus 7.
So I gave you 3 minus 7. We already got all the result. Remember that we got the result of this Vs, and we also got the result in terms of Vs prime. What were the results? Just remind me. Vs was 3 minus 7. That's the regular one. With respect to S prime,
1 1.
1.
1 1. You already got it. But let's just see how this formula works. So Ps to S prime. Now, if I am going to apply it on S prime, so these two I'll just remember. So 1 minus 2, 2 minus 5, acting on 1 1. Give me the result.
3 and minus 7.
3
Sir?
and minus 7. Yes,
So,
speak out.
so why did we write it in the form of column matrix?
What?
So why did we write it in the form of column matrix?
Why did we write what? I mean, the change of transition.
Yes, sir.
Yeah, see, there, so notation is always similar. Remember, since our vector is always defined as a column vector, right?
Yes,
Vector
sir.
is always defined in terms of a column vector. So the way we write, if you look into it, the first column of this guy is what? This is the column vector u1 in terms of what basis? In terms of our S. So this is a common practice of writing it. This is using a consistent notation throughout, that every time you are expanding it in terms of a generic vector, you are using this column vector algebra. One can do it using row vector algebra also, but then I mean most of the books don't follow that. Now that it has been, it is just like the charge is taken to be minus 1.602 of the electron. Yeah, you put electron charge as negative, right? And positron charge to be positive.
Yes, sir.
Actually, it is relative charges you could have taken otherwise also. But once it was taken, you have to be consistent. So in this way of writing allows me to write down my properties in a simple manner. So let's just go back on the previous page. The property which I wrote here, so let me use a different pen if I can. And this, the column vector approach allows me to write this kind of notation. Yeah. If I do not use it, then the notation will be changed. Then the matrix multiplication will not give me this kind of result. So I'm just getting consistent, nothing beyond that.
Okay, sir.
Okay. So one can in principle use something else also. Anyway, let's just build it again. Consistency works. So just like the way consistency is. So let's just use it. So we have done that. What about the other way? What about the P inverse matrix of this guy? So can we find the P inverse? S to S prime. So how to find that? First the determinant minus 5 plus 4. What about the components for the inverse? So this was the matrix 1, 2, minus 2, minus 5. First component.
Minus 5.
Minus 5.
And the other diagonal component will be changed. What about these two guys?
2
Minus 2 on top right and
Minus
bottom
2.
left 2.
minus 2 and then 2.
But this is interesting that it looks like as if I have interchanged it, but I did not interchange it. What did you do? You have just made this the negative, each one of that negative, right? So what will be the result ultimately? This. So since we have minus 1 outside, so I should put 5 and 2, minus 2 and minus 1. So that is required. Let's just apply my P inverse S to S prime on my original vector S. So let's just do that. 5 minus 2, 2 minus 1, acting on 3 minus 7, which was my original vector. What is the result?
1, 1.
1, 1, which is what you got earlier. Yeah. So instead of taking the longer route, I could have just come up with the matrix, which is what I call the change of basis matrix or the change of basis transformation. And then I could have applied it appropriately in order to get the result which we got last time. What happens to the linear operator? Can I use my change of basis matrix for the linear operation also, or the linear operator also? So here I am directly giving you the result, not deriving it, but I am going to apply it to see if what I am saying it does work or not. So let me just give you the result and discuss what I am trying to say. So given the linear operator in one basis, once my change of basis matrices are there, which is P S to S prime, and of course the inverse, then the linear operator in that new basis is given by this interesting relation, P inverse T P S S prime. Now, this is what I would like you to first work out, whether we are able to get it or not. So for this, I will say, let's just continue with our question, the question which we are trying to solve. And then we would try to see if we get the result or not. Later on, I will expand it to tell you the generic sentences to say the same thing in terms of the generic one. So let me just write down for you the matrices which you gave to me basically, and then we'll have to just write it. So what was P S to S prime? This was 1 minus 2, 2 minus 5. And what was P inverse S to S prime? This is 5, 2
5.
minus 2 minus 1, right?
Yes, sir.
So I want you to multiply these three matrices. That is P inverse 5 minus 2, 2 minus 1, then 2, 4, 3 minus 5, then 1, 2 minus 2 minus 5. And please solve it and try to give me the result.
8 minus
minus 8.
6, 11 minus 11.
So
11
8,
minus 11.
8 and
Minus 6.
minus 6,
Minus 6.
and
11
then
and minus 11.
11 and
11 and
minus
minus
11. And let's just compare with what we did on few pages back, which was what we got 8 minus 6, 11 minus 11 for this linear operator in this new basis S prime. So let's just go back, compare it. This is what you have given me. So the result of the previous pages which we got just by expanding the basis in terms of another one, they can now be written in terms of few basic ones. One, whenever we change basis from one to another and we come up with the matrix the way I wrote PSS prime, then that can be applied on this new S prime to give me, of course, S, or P inverse S to S prime can be applied to give me S prime. It works both way. Similarly, you can use the first relation, the relation which is given on the top, to find out any operator in this new basis just by using the matrix multiplication of this form. So it is not that the new basis, I mean the matrix, is not related with the old matrix. In fact, it is related with the old matrix with these matrices given like P SS prime and P minus P inverse of this. If I can just make life a little bit simple by writing P is equal to verse A P, this is very important transformation in terms of matrices, remembering that B is a matrix, A is a matrix which corresponds to this, and P inverse and P are the matrices. This is something what is called as similarity transformation. Now, what is similarity transformation? Similarity transformation says that if there exists a matrix like P such that two matrices B and A are related in this manner, the manner in which it is written P inverse AP, then matrix B is said to be similar to matrix A. In any case, I mean, right now we know that it is for the same linear operator that we got matrix B, I mean this 8 minus 6, 11 minus 11. And for the same linear operator, we had this matrix 2, 4, 3 minus 5. How they are related? They are related through this transformation. Now, why do we call that B is similar to A? This is because of a very important point, that whenever two matrices are related by this B is equal to P inverse AP, then determinant of B, which is of course can be written as P inverse AP, will be what? Remember, this is the determinant of three matrices multiplied with each other. Use the undergraduate level. So you can make a cyclic transition. P inverse A. What is P inverse? Identity.
Identity.
Which means that determinant of B should be equal to determinant of A. What about trace B? Same. Exactly in the similar way, you will find trace of A. What is trace of a matrix?
Sum of diagonal elements.
Right. So this is property 1, this is property 2, and there is this third property, which please tell me if you know or not. If I write this as B minus lambda I is equal to 0, what is this guy, what I have written?
Eigenvalue.
Characteristic
Yeah.
equation.
The
This
eigenvalues.
is famously called the characteristic equation
Equation.
for finding out the eigenvalues, right? But if you look into it, determinant again P inverse A P minus, I can just put, am I justified in doing the P inverse lambda I P?
Yes, sir.
Yeah, because it is basically written as lambda I P inverse P, but since lambda is number and I is an identity matrix, so I can just play around with this. And this is equal to 0, which means determinant P inverse A minus lambda I P is equal to 0. Remembering the property again, that I can take my P to first one. The eigen characteristic equation remains same. What does that mean? That the eigenvalues are same and the eigenvectors are same. So when we have two matrices related by this famous relation, which is called the similarity transformation, that there exists this P such that B is equal to P inverse AP, then determinant of the matrices are same, traces of the matrices are same, and the characteristic equations are same, which means the eigenvalues and the eigenvectors will be same. That is why it is said that B is similar to A, which means that the same operator which is represented by two matrices, these two matrices may look different to you, but they are similar in certain aspects. And quickly, can you tell me on the previous page, what is the determinant of my TS, the matrix operator in the S space, S basis? What is the determinant?
Minus 22.
Minus 22.
Minus 22. What will be the determinant of TS prime?
Minus 22.
Minus 22.
So I should use this space to write down determinant of TS is minus 22, which is equal to determinant of TS prime. What about trace?
Equal.
And the number is
Minus 3. Minus 3.
minus 3, which is equal to, of course, determinant, trace. And do the characteristic equation. Just write down the characteristic equations for both of these. Meantime, I should just take care of my. And the characteristic equation for first one, it will be 2 minus lambda minus 5 minus lambda minus 12 equal to 0 for one. And for another, it should be 8 minus lambda minus 11 minus lambda plus 66 equal to 0. Yeah, right? I mean, this is the way you solve it, right? The characteristic equation. So lambda is square, and then
Plus 3 lambda minus 22.
plus 3 lambda minus 22 equal to 0, right? This is for the
Yes.
first one or the second one?
For the first one, sir.
Okay. And for the second one,
So won't it be
Lambda
same?
it has to be,
Same,
but
sir.
I am still asking it so that, I mean, do it explicitly and see that it is coming out to be same, just to make
Yes,
sure.
it is same.
Of course, it has to be.
Yes, sir.
Yeah, I mean, that was the whole idea of doing the very generic property. What happens that when you do a very generic property, at times you do not, I mean, you are unable to correlate with what we are doing. I mean, right? I mean, in terms of the application. So I just wanted it to be done. Anyway, this leaves me with very important results for today's class, that there exists a special operation which we called as the change of basis operation and signified by P. Now this P is very important one, because this P will allow us to change from one generic vector to another one by using this matrix, or will allow us to change from linear operator in one space to linear operator in, I mean, in one basis to linear operator in another basis, again by the application of this famous similarity transformation. So this change of this linear operation is very important in terms of going from one basis to another basis. And even though the matrices look very different to us in terms of the components for a given linear operator, but they have certain important properties, and the most important one, which we call as that all the matrices representing the same linear operator, they are similar. So if I go to the third basis, then the third basis also, whatever matrix you will get, you will have the same determinant, you will have the same trace, you will have the same characteristic equation. So that is how the matrices which look very different to us, they are related, even because it is for the same linear operator, right? So this is where I would like to end my today's class. Tomorrow I will continue to build on my linear operators.
Sir, I have a question regarding the P matrix.
Yes, please go ahead.
Is there any restriction or a rule that actually P is the set of eigenvector? P is the matrix representing the set of eigenvectors for the matrix A?
Yeah, so what I will say is this. Tomorrow when we are going to do this little bit more, let's say in the expanded way, that I am going to do the diagonalization and eigenvalue problem, then I will tell you certain important things about it. Fine? That rather than answering your question that this P is restricted, no, I mean this P is only restricted by what? P is restricted by whatever number of bases you can come up with, right? You can always transform from one basis to another using this P. So you can have so many bases for a given vector space, in fact, infinite many, and this P can be built in those infinite many ways, right? You get the point?
Yes. So, sir,
Yeah.
P is not necessarily the set of eigenvectors for A, right?
I mean, you have yourself seen it, right? Uh, did it look like that? I mean, on the previous pages, when I wrote P as this, what, 1 minus 2, 2 minus 5. At this point of time, I don't want to say more than what we have done. Where it will be leading is what you are saying. So you are pointing me to some direction, but I will go to that direction again in my simple way, that I will take one stair at a time and I will reach there. What you are saying is going to be some sort of a backbone of quantum mechanics. But I haven't done that up to this class. So I will say that sentence in the class in which I will do it. And then I will relate it with what we have done here. Does it make sense?
Okay, sir.
Yeah, so you are pointing me to some place. I do not want to jump onto that. Okay, good.
Okay.
Anybody else for today's class? Yeah, I mean, it's an important one. Since you have already done it in undergraduate level, so you somehow know that. But okay, I mean, I just want to make it explicitly clear to everyone. Yes, go ahead. Ask question.
So everything is clear. You cleared about the transition matrix and but where is the role where is the role of Q inverse comes
Oh,
that
well,
you talked in
I mean,
between?
sorry. Yeah, I mean, that's a good point. I see. I mean, if you write I mean, it's not the role of Q. Q was written as what? Q was written as P inverse, right?
Yes.
So
Yes,
what
sir.
happens that students, I mean, since there is this Q which exists, so if I want to write B in terms of, so this will become QA Q inverse.
Yes, sir.
Yeah, you look at the book of Griffiths, for example. Fine. First edition or second edition, third edition, you will find that the similarity transformation where P is written as S, they will be showing S A S inverse as the transformation, similarity transformation. Griffith shows that. Whereas other books may be writing something like S inverse A S as the transformation. The role is to remember that one is related with other. In fact, in my notation, you can write A also. Now, what will be A in terms of B?
P P B P
B
inverse.
P
P
inverse,
inverse.
right? So in this notation, A will be Q inverse, B Q,
All right, sir.
right? The only thing is to use it consistently. That the problem comes that students look at the Griffiths book, then students look at the Shankar's book and other book, and suddenly they have this confusion that whether the similarity transformation is given by this SA S inverse or S inverse AS. It is the way I define it, right? I mean, as long as it is clear to you, that is the reason why in my classes, I write this P S to S prime, that my S prime vector, X prime vector is expanded in terms of S vectors. So this is, remember, this is how I started by saying this. Alpha 2 U2. So I generally have a tendency of writing these arrows, even though they look rather ugly, I mean, in terms of writing the whole sentences. But this just reminds me that I am using this notation. So one has to be consistent here again. I mean, this is just for consistency, not beyond that. As long as you remember that Q is equal to P inverse, the relations are basically can be written in terms of Q as well.
All right, sir. Thank you.
Yeah.
And sir, what all we are doing is in one vector space. Is this also true for linear transformation also?
Yeah, I mean, ultimately what we are doing here for the linear operators, you will see wherever I am using the properties when I am expanding one vector in two spaces, right? So currently what I am doing, that my n vectors remain n vectors because I'm in the same vector space, right? But if
Yes,
I'm
sir.
going from one vector space to W, let's say another vector space, it is possible that I may be going from n space to m space or p or k space. So one has dimension n, another has dimension k. So the matrices will not look n cross n in that case for the change of basis. In fact, any matrix, whatever matrix you take, linear operator matrix, that will have a different dimension. This dimension, which is fixed to n cross n in our case, v to v, will not be fixed to n cross n, but will be something n cross p or n cross q. Everything else will, of course, remain same.
Okay, sir.
You got the point, that since the two may have different dimensions.
Yes, sir. Yes.
Okay. Okay, so thanks for today's class. We will continue to build on to it.
Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you.